Very welcome to all of you, and I hope everybody is fine, enjoying the winters, enjoying the cold, and maybe now enjoying the sunny days that we have for last couple of days. So in continuation to our previous interaction, what I was talking about was probably we were in classrooms at that point of time, and today you are all enjoying your holidays. I hope you enjoy, but as a part of my assignment, I feel feeble and feasible that I should continue some of the important discussions that we have to go on with. And where we stopped last time, it was we were talking about these ladder operators. We were talking about the creation and annihilation operators, and we just wrote down the framework of these operators, and in view of those operators, we tried to calculate some of the commutation relations, and that can be a part of assignment as well for you, where you would like to calculate the commutation between the creation operators and annihilation operators. Say, for example, you would like to calculate this annihilation operator and the Hamiltonian operator. You can go with these kind of calculations, or you can choose on the creation operator a dagger, and you would like to calculate its commutation relation with the Hamiltonian of the given system. Now, what today's target is basically that we would like to go with the same formalism that we have for a harmonic oscillator problem, and we would like to devise the uncertainty relation from the framework of these creation and annihilation operators. So that should be the target, that we would like to calculate that uncertainty principle, as all of us know that the product of uncertainty between the position and the momentum of the particle is always greater than that of the Planck's constant. So that should be our target. So in order to move on from here, what we have is basically we have these operators. We have the annihilation operator. Come on. We have the annihilation operator A. And this annihilation operator is 1 by under root of 2m omega h bar, and then you have m omega x cap plus I p of x. So this is our annihilation operator, and we understand that this operator has a property that what it does, it takes your system one step down, and we can see that we automatically reach out to that quantization in harmonic oscillator problem. So what we have here is the annihilation operator. Then we have the creation operator as a dagger, that is 1 by under root of 2m omega h bar, and then here you have m omega x cap minus I p of x. All right, so these are the two fundamental equations. We would like to manipulate these equations to obtain some of the results based on the position of the harmonic oscillator problem and the momentum of the harmonic oscillator problem. And while doing that, we would automatically reach out our target that we have here, and the target is to attain Heisenberg's uncertainty principle from these creation and annihilation operators. So what we would like to do next is we can see easily from these equations. If I add up these two equations, when I add up these two equations, what's going to happen is the iota px and iota px term is going to die. So we'll be left with these first two terms. So we will have 2 times the first term that we have in the brackets. Okay. So what can be the next thing that we can do here is I'd like to go on the next. So what we will have 2 by under root of 2m omega h cross, then you have m omega x cap, and this must be equal to a cap plus a dagger. All right. So what we have here, we have the summation of these two operators, and from this equation we can probably calculate the position operator. So what will be our position operator? It will be x cap. So this term will go up. This will be 2m omega h bar, okay, divide by m omega, and 2 also, right? This will be multiplied by the annihilation operator and the creation operator that we have. And we can manipulate this thing like x cap will lead us to, this can be written as a single root. So this will be 2m omega h bar divided by, so this will become 4n square and omega square times a annihilation plus a creation. So here you can see that we have calculated the position operator, and we can expect the cancellations. 2 and 4 will cancel, this m and square will cancel, omega and square will cancel. So x cap, for x cap we will be left with come on, it will be h bar by 2m omega. So I would like to write this h bar by 2m omega. This whole thing is in the roots, and in the left hand side you have x cap, and you will be multiplying this with annihilation operator A and the creation operator A. So this is our first result that we are interested in, and we would like to evaluate this result immediately, because then after that we will move on for the momentum operator in terms of these creation and annihilation operators. So that will be our target. But before going there, there are 2 ways. One is, okay, let's go with that first. So what can I do here is, I would like to if I calculate the expectation value of this position. So what will be that expectation value for, say, the state K, and you have x cap, and for the state K. So the evaluation of this bracket will lead me to calculate the expectation value for the position operator of the harmonic oscillator problem. So here, instead of x cap, I would like to substitute this whole thing. So what you'll get here is, you'll be left with K, and you will have, you will have h bar by 2m omega. Then this will be multiplied by a cap plus a dagger, and you will close it, and then you are back with your state K. So this will lead us to have the expectation value of the position operator. And what we would see here is that we can use the property of brackets. So we will have 2 independent formalisms here, but this constant term, it has a root on it. This constant term will be outside this bracket. So what we will have is we will have this this expectation value for the position will lead us to under root of it is h bar by 2m omega. Okay, so in first case you will have k, and inside you will have the annihilation operator k, and plus in second case you will have k. Now you will have creation operator a dagger and k. That should be the case. Now, from our understanding of basics, basic orthonormal properties in quantum mechanics, as we know that we can represent them in terms of the Kronecker delta, and if the bra quantum state is different than that of the ket quantum state, then that whole bracket will collapse. So we can see here, see this is annihilation. Now annihilation is taking you k, when you will add this operator on k, what you are expecting from it? You are expecting from it, to go from the state k to k minus 1. So this will immediately be equal to 0 because the two states, they differ. If they are similar, then this combination can be equal to 1. And if you look at this, the second part of this, what you have the creation operator. The creation operator will take your state k, it will take it up by 1. Now in both the cases, we have the difference in the ket and bra. That difference is immediately taking them equal to 0. So from this mathematical procedure, what we obtain is that the position, the expectation value of the position is under root of h bar by 2m omega. It will be multiplied by 0, so this is equal to 0. So this part is evaluated. Now we would like to evaluate the next part. And in next part, what we would like to calculate is the expectation of the square of this position. So let's go with that argument. So now we want to calculate the square of this this position operator that we have. So what will be that written here? That will be written like k, and then you will have x square, and then you will have k. This is what you will obtain. Here, for x square, I'll have to use the square of what we have. So what we have is k, then you have under root of h bar by 2m omega. Okay, for x we have a cap plus a dagger, and this whole thing as a square, and then you will have the state k. Now one thing is clear from this, that the square and root will cancel, and you'll be left with this h bar by 2m omega. So h bar by 2m omega will be left here because the square and the root will cancel. Then inside you'll be left with a cap plus a dagger, the annihilation and creation operator whole square, and you will be back with k. So what we are expecting from here is, what we are going to do here is that we would like to take the product, but one thing is clear, that we have to take this product in order, because everything depends on order. If we do something wrong in order, then we will have inconsistent results that we'll be expecting from it. So what we will be having is, here we have square of it. So what we will be having next is, h bar by 2m omega, and inside I'll have k and the ket of k, then plus, no, there is no plus, then I will have a and a plus a dagger plus a A dagger plus A dagger A, and you will have your own ket, the ket of K. And using the property of brackets, so this is what we are calculating here basically. So using that property, what we will be obtaining is something like this. This is h bar by 2m omega. So you will have K and A, and this is annihilation operator. You will have your K back, then you will have plus K, you will have creation operator, and then you will have K, and then the third term will be K, then you will have annihilation operator and creation operator, and you will have K, then you will have K, you will have creation operator, annihilation operator, and you'll be left with K. So this kind of document we are going to obtain by using the properties of brackets, so that you have these independent terms falling in each bracket. Now we can boil down this result in a very simplistic fashion, because here you will be using annihilation. It will lead us to K minus 1, then it will lead us to K minus 2, then there will be that orthogonality, and this will be equal to 0. And similarly here it will go to K plus 2, and this will also be immediately equal to 0. Now looking for this part of the problem is you have x cap. So x cap will be h bar by 2m omega. Okay, so what about this? Now you can see that if I use the creation operator on the state K, it will take it to K plus 1. But once it goes to K plus 1, I'm using the annihilation operator. The annihilation operator will bring it back to its original state. So what you are going to be left with here is, you will come back with K and K. This will be the first thing. Now looking for that, okay, what we will have here, we have K. Then first we are using the annihilation operator. It will take your state down by 1. Okay, then using the creation operator, it will take the state up by 1. So you will be left with K. And the value of this is equal to 1, and the value of this is equal to 1. So 1 plus 1 is equal to 2. So we will have h bar, twice h bar by 2m omega. So we should write down this result here. So what is that? X cap will be twice h bar by 2m omega. All right? And this 2 and 2 will cancel, and you'll be left with h bar by m omega. So this is our result for x cap. Now, in a similar fashion, what we would like to do is, if you remember in the very first equation that what we have, yeah, what was that? Come on, no. Yeah, I don't know. Yeah, these two equations. If you look back into these two equations, you can see now, if I subtract the two, what's going to happen is this will turn into plus. So if this will turn into plus, these two terms will cancel. So you will be left with 2 iota p of x. So the result that we will be obtaining is, let me go back to my point, is when you will subtract the 2, what you will be obtaining is, you will be obtaining 2i p of x. Okay, what was outside? It was, I forgot it. What was outside? Yeah. It is 1 by under root of 2m omega h cross. 1 by under root of 1 by into 1 by under root of 2m h bar omega. Okay, so this thing will be equal to, because you are subtracting these two equations, and that subtraction will lead us to A annihilation minus A creation. This is what we are doing basically. So from this, what I would like to calculate is the momentum operator along x. And we can see here this Px cap will be equal to under root of 2m h bar omega divided by 2 iota. And this will be multiplied by a cap minus a dagger. Now a cap, I mean here, it's not a unit vector, it's an annihilation operator, and a dagger is a creation operator. So we can easily see here that this iota can be taken on the top, and this 2 can be taken inside the root. So when you take it inside the root, 2 will become 4, and 2 and 2 will cancel. So it will be something like, come on, is this the end of the story? Oh no, but how? I don't know. This should not be the end of the story. It's only 9 pages per. I am not sure about it. Okay, so where we are here. Okay, so I should use the eraser tool. I don't know where is that. What's this? Yeah, what is this? Let me check it. No, this is, yeah. Oh no, yeah, it's going. I am testing it, I'm not sure about it. Oh no, it's happening freakily. Okay. Come on, it's going on. It's taking a lot of time. Okay, so this is the only way, because this is the last. I thought it must be, I was assuming that there will be infinite number of pages. There will not be any end of these pages. Now we have to compromise on the constraint that we have here. So what we can have is, we will have this, oh no, I have to go back to this now. So what we'll have is Px cap, this will be equal to under root of, this will be 2m h bar omega by, so iota will make it minus, so I will go on the top, because you'll be multiplying and dividing by iota. That will lead us iota in the numerator, and you can incorporate the negative sign. So inside you will have 4. And then you have your own story, then you have a cap minus a dagger. This is what we have. This 2 and 4 will cancel, so you'll be left with this result. So this is my Px, okay? This is my Px, and I want to find its expectation value, as I did in the previous case. Yeah, come on. I don't know what's going on. This is some kind of magic going on. Okay, so what am I interested now is, I'm interested in to calculate the expectation of the momentum operator. That will be K, that will be Px cap, and K will be there. And what you expect from here is, you will have K, and for Px, I'll be using this minus I under root of m h bar omega by 2, and then I have my own story, the annihilation operator and the creation operator. I'll close in, and this will be my K. Okay, so evaluating this bracket will lead me to the expectation value of momentum. And we have done it repeatedly using different approaches. But here we are using an approach of ladder operators to reach out to the very fundamental basic principle of the universe. And that principle tells us, you cannot, whatever you do, whatever way you approach me, you cannot know exactly who I am. And that's the beauty of this negative principle, making us realize this uncertainty of the universe. It is embedded in the fabric of this universe. So what can we expect from this? So here we can directly look for the result for this equation. See here we will have the two terms. One term will be in terms of annihilation operator, another term will be in terms of the creation operator. You will have two brackets as in the previous case, and in the first case, say a dagger, it will make different brackets, so that will be 0, and this will also be 0 because you will have two different brackets. So expectation value of momentum will be simply equal to 0. Now we want to go with the next part. The next part is I would like to calculate the square of the momentum operator, the expectation of the square of the momentum, and that should be my job. So if that is the case, then you will have the same situation, but here you will have square and here you will have the square. Okay, so this is how I can manage to use the board, because the story is ending here. There is no additional, oh sorry, it is there. Okay, I was not aware. Okay, so I had to use plus. I forgot to use the plus. I thought using this arrow will lead me to the next page. So what's going to happen now is you will have the square of this thing, and this square will make this iota square will be minus, and minus square will also become plus, and this term will take us to to a positive number. So what will be inside? Inside you will have, first I would like to get this, the square and root will cancel. You will have mh bar omega by 2. Okay, you will have mh bar omega by 2, right? This will be something outside, and inside you will have k, then you will have a cap minus a dagger whole square and k. This is how we can manage it, and we know we are calculating the square of momentum expectation value. This is what we are trying to calculate here. So obviously you will have that a minus b whole square, but you have to keep in mind the order of that multiplication. That will lead us to m h bar omega by 2, and here you will have 4 terms. So you will have k, and you will have a, this will be the term number 1, and then you will have plus k, yeah, and you will have a dagger, and then you will have k again. Okay, then you will have so you will have a dagger minus, okay, and minus a dagger a. Okay, so both of these have to be decorated by the brackets. So minus will be out, and we know it must have k and k and k, and all of these things are clear to us. But one thing I want to make sure is that what we had here, we had iota here. So iota square will give us minus 1, but there is another minus that is existing inside the bracket. So that minus will become plus, but the square of iota has led us to minus. So minus sign should be outside this term. And now immediately I can say that this term is equal to 0, and this term is equal to 0, and this minus will go inside, and it will make everything positive. So when it will make everything positive, you will have m h bar omega by 2, and the result here will be 1 plus 1. So that will be 2 and 2 will cancel. So you have got m h bar omega. So this is your px square. So now I can write down the uncertainty in terms of the position. I can write down the uncertainty in terms of the momentum, because uncertainty is basically the measurement of standard deviation. So what will be that? So I will have delta x. And what will be delta x? That will be under root of x. That will be under root of x squared minus x whole square. So this will be our uncertainty in the measurement of the position, and delta px will be under root of px squared minus px whole square. And immediately you can see that this term is 0 because we have calculated the expectation value of the position operator, and this term will also be equal to 0 because we have already calculated the what we call as the expectation value of the momentum. So what we can do now is we can multiply these two, delta x and delta px. What will that lead us to? That will lead us to the under root of x squared times px squared. And this will be the outcome. Okay, so all I have to do is to use the square of position operator, its expectation value, the square of momentum operator, its expectation value. So I would have to go to that now. I would like to see what was that. This one is mh bar omega. So I would like to go ahead. So this is equal to under root of mh bar omega. Maybe I committed some mistake, I'm not sure. There might be some minor mistake. Now let's see back here for x squared. For x squared we have, oh no, yeah. For x squared what we have, it is h bar by m omega. H bar by 2m omega. Okay, so this is h bar by 2m omega. So you can immediately see here, maybe even if I have committed any mistake in terms of numbers, that doesn't make any difference because we are achieving our base. Here I think it is not 2, it is only m omega. Here is no 2. I would like to cut it. So this is not there. Okay. So it's only h bar m, h omega. So you see this m and oh no. So here you have m, this m and m will cancel, omega will cancel. So you will have h bar whole square, square and root will cancel. So what you will have here is you will have your beautiful uncertainty principle, delta px, and delta x is nearly equal to h bar. And what is h bar? H bar is nearly, it is h by 2 pi. Okay, so this is the result that we were looking for using creation and annihilation operators, and this is nearly equal to h by 2 pi. Okay, so this is what I wanted to share with you, students, and maybe I committed some mistake, I'm not sure about that. If I have done it, the beauty is to actually come out of that mistake which I have committed here. It's your job to work on that, and you could see the beauty of these ladder operators, which we sometimes call as creation and annihilation operators. You could see that how beautifully you are achieving a result that's very fundamental of nature, and that result is Heisenberg's uncertainty principle. And what uncertainty principle tells us is that you cannot, if you are accurately measuring the position of a particle in one direction, then certainly you cannot accurately measure the position of the same particle, which is not the case when you are dealing with the macroscopic bodies, when you are dealing with football, balls, even aeroplanes, planets, moons. Wherever you deal with macroscopic objects, you don't have those constraints. You can exactly calculate the position and momentum of a particle, but that's not the case when you go down to the quantum mechanical scale, a scale where we have living atoms, we have living molecules, we have living electrons, we have neutrons and protons. In that framework, the laws of classical physics does not work. They fail to give us the results, and the biggest opposition in the framework of quantum mechanical world is Heisenberg's uncertainty principle. That is, you cannot measure the position and momentum of a particle at the same point of time along the same coordinate. So I hope you like this. I want you to work on this lecture, and I want you to look for I want you to discover some other important results from using these later